This is one of the tricks that we can perform on the watchmaker's lathe. It's very easy to do this with handheld tools. That is, the handheld graver, the drill bit, in a pin vise, and we come out with an excellent result. This next parcel of Huckabee Clock Talk will deal with the basic disassembly and assembly of a small trapeze type movement, and this is time only. It's an 8-day movement, very nice little clock, German made, and we'll look this over, we'll disassemble it and see how that the clockmaker disassembles, inspects, and repairs if necessary, and reassembles a clock movement and places it into operation. Let's look at this. This is the pendulum rod, and below that is the crutch that we will look at a little later. This is the suspension spring. This is the chop, or the support for the suspension, and the pin for the spring. Let's pull the pin and begin to disassemble here. We have the pin. This is a small taper pin. Possibly we can pick this up in the camera right here, and we'll drop this into a container. I use some little sardine cans. That's about the nicest little container that you can have for clock parts. We'll slip out the suspension spring, and let's look at the spring. We'll catch this in a tweezer now. The suspension spring has a cross pin that is used to hook up to the pendulum rod, a cross hole that's used to lock it into the chop of the movement. We'll set that aside, slip the pendulum rod down crosswise, and we have that in our hand. Now, let's think about how do we hold this while we're doing various and sundry work. Here is a tool that I made many years ago. This is a similar tool to this is available commercially. We drop that on the plate, take a scriber, lock it up. What this amounts to is something like little C-clamps with a long stud on them, and we can drop on about 3 of these, and that will make the movement sit on its back for handling here. The next thing that we need to do is to be concerned with the power that's in the mainspring. If we lift the plate from this movement with the mainspring under power, it's disastrous. That's probably the end of the movement. So let's see what we do. Let me turn around and see if we can locate in the camera the click on the ratchet wheel. Here's the click. This is the click spring, the click, the ratchet wheel. And this is the thing that holds the mainspring wound. We use a let-down bench, let-down key. This has a socket. One of these sockets fits the winding arbor on the clock. We take this, slip it on the winding arbor, and we will release the click from the ratchet and let the mainspring down. Hold this let-down key sturdily, pull the click out, and we let the mainspring down. We check to see that the mainspring is completely down, and it is. Next, let's remove the dial works. The dial works is the 3-to-1, 4-to-1 reduction gearing that drives the hour hand. We'll turn this little clip right here around, and with a plier we'll slip that clip loose, pick it up with a tweezer, and then lift off these wheels. That's simple enough. Now let's remove the mainspring barrel. Looking, this is the barrel containing the mainspring. In this particular movement, there's provision for removing the mainspring barrel without removing the plate from the movement. That's because that there is a slot right in this point in the movement, and there is a ring around, a machined ring around the arbor so that we can get that barrel out. To do that, we take out the hold-down clamp and use a screwdriver that fits the screw slot perfectly. The screws in this particular clock have been abused in time past. Let's take the screw out, pick that up. We lift the clamp, pick that up, and we can pick up the winding ratchet. Now, if this had been released, if this ratchet had been removed, this had been released with the mainspring under power, it would be disastrous to the movement and possibly highly probably do irreparable damage. Now we lift the barrel forward, that is toward the front of the clock, and we gently slide out the mainspring barrel. We have the grate wheel on the end of the barrel itself, the barrel cover, and through this hole we can see the turns of the spring. This is the winding arbor, and I don't know if we can see, right here is the slot that permitted us to withdraw this arbor through the slot in the plate. We'll lay that aside. That being heavier, we'll not place it in our small container. What is the next thing that we do? Well, let's just take the escapement anchor out, and in this particular movement we must loosen the screws here, and in doing this we lose an important adjustment in the escapement. This is the bridge that sets up down, sets the engagement depth between the escapement anchor and the escape wheel. When we remove this bridge, when I loosen these screws, we totally lost the escapement adjustment. That is the depthing adjustment. It may behoove you, if you have a problem with the escapement and you have reason to believe that the escapement is in order before the movement is disassembled, to take a small sharp scriber and scribe just a tiny little mark right under this bridge, and that would help you to return to that position. But being that we will discuss the escapement adjustment, there is no point in us doing that on this particular movement. We take out the screws for the sake of, well, I have a problem with my hands in the way in the camera, but we'll just drop the screws on the table for the time being. Get those into the container, and here is the bridge that we're speaking of. The bridge, see if we can get this into the view in the camera. The bridge has a pivot hole right at this point, which is for the escapement anchor's arbor, the pivot of it. These are elongated holes such that this bridge can be adjusted up and down. As we turn here, we see the, see if we can find a place here. I don't believe we can find a place that we can see this in the picture, but this has the slot that receives the suspension spring and the cross pin. At this point, we can lift out. We can lift out the escapement anchor. Let's look at this. This is a strap type escapement anchor. It really doesn't look like an anchor. It's commonly called a verge, anchor, quite a number of other things, most of which are really misnomers. But this is highly polished, very hard steel. It looks similar to that in some of the old American clocks, but when this type of escapement is well made, well polished, it is a very, very reliable escapement. The crutch out of the rear side is friction fit. This collet is friction fit onto the shaft and can be adjusted. You can see that I can turn this through a wide angle, and that destroys the beat adjustment totally and completely, and we'll find the way back when we reassemble the movement. Looking a little further, we find this particular one has the pinion, which to the watchmaker is called the cannon pinion. This one, I suppose, is really not a cannon because it does not have a tube on it. It's hard pressed onto this shaft and not readily removable. That says that we cannot remove that shaft from this plate readily, and really there is rarely ever any valid reason to do so. Next, let's disassemble the gear train and take a look. All right, this particular movement, because that this wheel, this shaft, cannot be readily removed, we need to work front side down. Many movements work back side down, many work front side down. This one needs to be worked front side down. So let's move our feet, the feet of this movement, to the other side. We lock this up. That's simple. We lock another up over here, and let's put the third one about halfway up the plate so that this will stand on 3 feet very sturdily, like this. You may have observed this is a different distribution from what I used when I had them on the back side. When I had these feet on the back side of the movement, I had the mainspring barrel in the movement, which is one of the heaviest pieces, probably the heaviest portion of the movement. And I had the feet moved further down toward the heavier weight so that it would sit firmly with that heavier weight. Now, as we go here, this looks like we've made a mistake, but we really haven't. The nuts here that hold this movement together, 4 of them in number. Lost my way in the illustration here. These 4 nuts in number are on the down side. So let's take these out first. It's always nice to use a wrench on this type of thing, because the use of a plier scuffs the movement, damages the nut and whatnot, and on top of that, the wrench simply is the easiest tool to handle anyway. I'll run these off by finger here. You might normally use a spinner wrench on this, that is something that has a socket in the end, looks like a screwdriver handle, and spin those off at a savings in time. However, if I do that, I have, in this particular case, I have my hands in the camera view. Place the nuts in our storage tray. Now let's disassemble. This is movement backside. We lift up the plate, lift up, we ease this so that we pull up straight so that we don't have any stress on the pivots, and off comes the top plate. Well, this is really the rear plate. If we look on the back side here, this it says made in Germany. It says no jewels, unadjusted, the usual things that's there, and a part number or a model number. Looking on the plate, we find some scratches here. That scratch seems to have been the result of this being disassembled in time past, of sliding this out and the end of this arbor has scratched the movement. This is a nice looking little movement. Now, let's look at the gear train. See if we can get this, try to dodge some of the light reflections. Our great wheel set there. This is the great wheel. Drives into the pinion that is underneath the second wheel. We call the great wheel the first wheel. The first wheel, this being the second wheel. Let's lift that out, set it aside. Let's lift out the second wheel. Now, look at the second wheel. It has a beautifully finished pinion on it, a highly polished pinion, an arbor, and a nice machine cut gear. That is a very durable, very fine piece. Remember that when we were looking here, we said we cannot get this shaft out because we have a press fit on this. Now that can be removed. When I say we can't get it out, doesn't mean that it's impossible, but it cannot be lifted out, and at this point in time there is really no reason that we should. So let's turn back over and look again. I'm holding wheels in place with my fingers. We would call this the great wheel, or the first wheel. We called this the second wheel, and consequently this wheel here is the third wheel, the fourth wheel, the fifth wheel. Third, fourth, fifth wheels, if we want to use that designation. In more common vernacular, we call this the center wheel. That's called the center wheel because its shaft is the center of the dial. It carries the minute hand. The minute hand turns 1 revolution per hour. It can turn no other speed if the clock is to keep time. So the center wheel in this particular movement is the third wheel. This is the fourth wheel. Let's lift out the fourth wheel. Center wheel drives into the pinion of the fourth wheel. The fourth wheel then drives into the pinion of the escape wheel. The escape wheel we just identified as being the fifth wheel. Fifth wheel in the train. This is this particular wheel. The cut of the teeth shows that it's a recoiling escapement, and it is the classic type of tooth form. Now let's look a little further at this. If we're careful, we can clean this movement, and we can lubricate it and whatnot with this wheel in place, and that says that there is not a valid reason to press that pinion off and to pull this wheel out, unless we have some reason to make a repair on it. Let's see if we can get the color on this a bit. This is brass, it's yellow. The wheel is brass, it's yellow. This cross right here is spring steel, and it is more of a bright color. That is the device that permits us to set the hands. I don't know how tight this is. Let's see. I don't seem to be able to. There we are. We can turn this on the wheel. I've turned it to a new position on the wheel. But when the hands are hooked up, this shaft, the minute hand on the front of the clock, turns inside this wheel. It slips. This is the spring that has the friction to permit that to happen. Now, how do we go about a reassembly? One of the problems is how do we get all this back together? Well, to the beginning clockmaker, this is the idealistic movement to begin to learn to disassemble, reassemble, and adjust. Idealistic because it is well made, it's not very large, the mainspring is in a barrel, and that says that we don't have to cope with mainspring problems unless there is valid reason to remove the spring from the barrel. The no strike train is a minimum number of wheels, and it goes on and on. This is the clock movement. As a matter of fact, this movement belongs to the American Watchmakers Institute. This is one of the movements that's used as a student practice movement. This has been through the hands of many, many students. It has been well cared for, with the exception of some of the screw slots, with the exception of some screw slots that have been badly used with improperly sized screwdriver, which has burred that up a little bit. This movement looks essentially new. It has been disassembled, cleaned, polished, whatever, as a practice through many students' hands. And I would commend the last student that had this in his hand for the polish that he has on these pieces. The question is, how do we reassemble? How do we reassemble a movement? Well, you place all the parts where they fit. That's about the simplest statement that you can make. But the question is, where do they fit? Now, I disassemble this without regard to where a piece went, where pieces are placed, without regard to escapement adjustment and these type things, and we'll go back together getting this back in order. In the first place, the pieces fit in logical order. Let's look at the great wheel. That's the largest one. Look at the second wheel, which is the second largest one. The center wheel, which is the third one. We'll leave a little space there. The fourth wheel, our center wheel, will go here, and the escape wheel. So this is the order that we find these things in the movement. Now, we don't have to assemble them in this order, but this is the way that we would pick them up if they were randomly here on the workbench. This is the way that we would pick them up and reassemble. Now, we have a very easy movement to assemble, because we found that we can place the great wheel and the barrel in the movement last without any problem. So let's begin. You look around here at the pivot holes, and it looks like this plate is just full of pivot holes. Most manufacturers manufacture a variety of movements with a basic plate blank, and it says that most of these holes have no use in this application. We find the four corner pillars. We can find that easy. This is the great wheel. This is the center wheel. So that tells us that this wheel goes somewhere between great wheel and center wheel. It's second in size. Turn over and let's find where that can go. We look around here. There's the hole, and we only have a single hole. Here is a hole there, but we find there's something in it on this side. That's the click spring. That hole is too tiny for the pivot, so it becomes intuitively obvious that this wheel goes there. All right? How did I pick that situation? What tells me that it does not go this way? It will drop in there at that point. Well, the real reason is there's nothing for this gear to mesh with. Here's the pinion. Right here is the pinion that it must mesh with. So if we look at this with a little logic, it must assemble that way. Great wheel. The great wheel, mainspring barrel, will go here. Second wheel, third wheel. Fourth wheel comes next in size. We look about this. Let's see what we have. It will be driven by the center wheel. We're progressing up the train, and it must be driven into this pinion. That says this wheel cannot go this way, because it's impossible for that wheel to drive into this pinion with it turned in this position. So we pick it up in our hand here. All we have to do is to look around this area, and find the pivot hole that it goes in. Very simple, right there. And the escape wheel. Which way does the escape wheel go? Can it be this way? Is it possible that we assemble it this way? No, the pivot cannot mesh with that wheel. The escape wheel must be turned over like this. And we look for the place, and we find the place is there. So that's the thought process. That's the thought process that we have in assembling a movement. It doesn't make any difference what it is. That's the thought process. If you have a striker train, if you're not vividly familiar with it, you might keep the striker train pieces separated from the time train pieces. The striker train pieces have identifying features that time train does not have, and vice versa. But in this case, we find that is relatively easy and simple. How do we get all this back together? The problem, most any lad that has torn up his grandma's broken down clock knows that he can't get it back together. You find out that the spring gets too big, or you can't get all these pivots through the hole at the same time, or whatever. Well, that's the way it is with a clockmaker, except you learn to live with those problems. Let's set the top plate on, and we do this gently. We drop the pillars in the particular holes that they go into. Now, at this point, there are none of these wheels that fit. None of these pivots are coming through the holes. So we have to start somewhere a progression of this work. Let's try right here. And I slipped the second wheel pivot into that hole. And I'm holding this corner of the plate very lightly. We'll reach in here and see if we can get the center wheel in there. And now I've slipped the center wheel pivot into that hole, and no, it dropped out again. Let's try it back in there. There we are. We have the center wheel pivot in that hole. Now move my finger up with the pressure just ever so slightly here, and let's see what we can do here. It looks like the escape wheel is longer, so we drop it in next. And the fourth wheel is the last one. I'm going to have to get my head under this camera to see this. There we go. There we go. That's all there is to it. Can you see those wheels spinning? That's all there is to it. It's together. Don't lose the grip or you have to do it over again. Okay. We find this little container is very nice to begin with, but it's not so easy to get small pieces out of. So let's do this. We'll pick up the nuts. We'll spin the nuts on here. Spin these on by hand. Now I'm disregarding the getting fingerprints and whatnot on the movement. When we repair a fine movement, it might behoove us to assemble this with a cotton glove or a plastic glove. Hold the movement by the edges. Don't put a fingerprint on it. I have a clock in my living room that was given to me for 25 years of service by IBM, which is an Atmos, all gold-plated. I had to replace the suspension ribbon in it a few years ago. That's one of the most difficult jobs that you'll ever do in your life, because everything that you touch on that gold leaves a fingerprint, and it's just not an easy job to keep the fingerprints off of a fine clock. That's another problem in workmanship, however. Now, if you noticed, while I was talking here, I was loosening these nuts, pulling these two down fairly close. Now, the reason for that, I want to be able to separate this plate at this point just a bit. Down in the bottom, see if we can get a view here. In the bottom of this movement, right about here, is some scratches. Those scratches was a result of this arbor being ever so slightly long to load in there. I want to be able to lift that plate just a slight amount to slide this barrel back in place there. All right, I'm having a little trouble hooking that up for some reason. There we are. We're in place now, and I did not contribute any additional scratches to that section of the movement. That's the reason I lifted that plate. I suspect the arbor was a little long for the plate spacing, as seeing the scratches that was there previously. We snug up these nuts like this with a little wrench, and we're together. Now let's do a little inspection routine here. See if we think this movement is going to run when we reassemble it. My arbor slipped out of place there. That slips out of place because I don't have the hold down, don't have the ratchet and the hold down on here yet. We're back in place. Well, let's give this a spin and notice that train is running very, very free. Now, if we spin this train until we have cycled every wheel in this movement around at least one revolution, and there's no indication of a bind, that's an indication of things are good. But here's the item that I would like to speak to a little more careful. Let's take this wheel right here. This is the fourth wheel, and I shake this to see that it has in play in the shaft, in the arbor. It does. I take the escape wheel and I check the in play in that. I check the center wheel. We have in shake there. I check the second wheel. We have it there. And for the best check, we'll need to check the winding arbor after we have added the ratchet. So we find that there is no bind in the movement. There is no bind in the in play. I've dropped this out of the pivot hole in the back. There, we're back again. Let's place the ratchet on. Turn the click around. Turn it around to its appropriate place. And at this point, if we take a strong tweezer, the short stubby is very strong, we can lift that click spring and move the click back behind it. I don't know if we can get a view of that or not. Possibly we can right here. You'll notice that the spring is over the top of the click rather than to the back side of it. Put this back in for about the 6th time, I suppose. There we go. And we'll install the winding ratchet. Well, that click is gone as the tweezer. That click points this way. The click points down this way. That says that we want the teeth of the ratchet to point up that way. So we drop the ratchet on as such, and we'll pick up the hold down and the screw that goes into this and a screwdriver. Well, we missed the screw hole there. Let's try again. I have a problem with these tweezers. Look like most of these tools that I have here are becoming magnetized. In a clock talk here, and one of these in the future, we'll deal with magnetism and how to remove that magnetism. It's a real gross nuisance. In some corners of the business, we find that magnetized tools are sold supposedly with some intrinsic value, but I've never found that to be the case. Tools that are totally non-magnetic are by far the easiest to use. We have this perfectly free now. We still do not have the click engaged, But let's slip the spring off so that we can wind, that's the click spring, and let's wind the mainspring. Let's wind this mainspring about, let me get to the point where that I'm sure the arbor is hooked up. Let me move this out. Okay, now let's pull up about 1/4 of a turn on the mainspring. That's about 1/4 of a turn. That was about this much on my, and notice the train is running totally, completely free. This is the idealistic situation that we would look for. We have in play and in shake in each of our gears. We have a totally free train, and we can spin this situation with just 1/4 of a turn on the mainspring. When we get into some gearing, we'll see what the how many turns of a mainspring is required to operate the movement for a week. But I imagine that 1/4 of a turn is possibly no more than an hour or two or so on this particular movement. All right, let me make another setup here, and we'll look at adjustment of the escapement. And let me take a direction on adjusting this escapement that is not necessarily one that I would recommend to the beginning clockmaker, because there are simpler things to do. But I want to show the use of the depthing tool in escapement adjustment. Now, to use the depthing tool in the escapement adjustment, I need the escape wheel in my hand. I need the escape wheel in my hand. And I need the escapement anchor in my hand. So let's take the escape wheel out of the movement. We'll retract some of the things that we did here a few minutes ago and show you how easy it is to get this out. Note that I slack the nuts on the backs, on the lower side of the movement. I have the mainspring. Let's be sure that mainspring is totally down. It's totally down, and I'll lift this plate ever so slightly, reach in here and take out the escape wheel. Simple as that. Now I probably, let's see. Yes, I did. I dropped the 4th wheel pivot. 4th wheel pivot is out of position in there now, but that's of no consequence. Let me pause here, and I'll locate the depthing tool and be back. We've returned to the Huckabee Clock Talks, and up until this point on this tape, I was having problem with my tools, with the magnetization of my tools. I don't know whether you realize that or not, but it was bothering me pretty badly. You see this pin right here? This is the pin that holds the suspension spring in place. Can you see the? Don't know whether we can find a place we can see that or not, but I'll pick that pin off right here with this tweezer. Both of these tweezers are magnetized. I can't lay the pin down, is what the trouble is. Also, I was having problem with my scriber, and I don't know if some of these other, that is not magnetized. That seems not to be, but just to stop the nuisance from this situation, we'll talk about magnetism just for a moment in the midpoint of this discussion. This is a watchmaker's demagnetizer. I got a hold of that second hand when I was an apprentice watchmaker more than 40 years ago, and I have no idea who built it, but I know one thing, that most watchmakers today decry this as being a deplorable, low technology, or some unit that is of not much value. But let me show you here. Let's find something that is magnetized. This tweezer will magnetically lift that arbor right there. That will just literally drive you up the wall when you're working on a piece of equipment. Now, how does the demagnetizer work? If you understand the theory of the demagnetizer will work for you perfectly. If you do not understand the theory of it, you probably won't be able to make it work at all. That's the way it is. The theory is very, very simple, and once we grasp that idea, then we'll find that there is no better demagnetizer made than this. Now, I was using the word magnetizer, demagnetizer, one and the same. We can use this for either function. This coil, many turns of coil of wire, connected to the AC power source. As such, with alternating current, the magnetic field, which is on this axis of the demagnetizer, is first north to this end, and then north to that end, and to this end, and to that end. And this alternates every half cycle through the 60 cycles per second of electric power that we have. The energy that this consumes is fairly high. It's in the order of 400 or 500 watts. That says that we cannot leave the power button on more than a few seconds, because this would then become a heater. It would burn up from that. As a matter of fact, if you keep the button down for 10-15 seconds, this becomes quite warm to touch. Here's how it is used. We slip the object in here. We see that this is magnetized at the moment. We're not holding this in the grip of the tweezer. It's magnetized. We slip this in here, and we depress the button, and we draw this out. As we draw it out, the polarity, the magnetic polarity in this tool is reversed, 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 reversed. 60 times, 120 times a second, because it alternates. It goes through a complete cycle of positive, negative, 60 times a second. As we pull this out of the coil, it becomes weaker, 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 weaker. Magnetically, we're doing the equivalency of swinging a pendulum that has no movement on it, and in a short period of time, the pendulum oscillation swings down to zero. That's what's happening magnetically, so it's necessary to insert the instrument, push the button, pull it out to a distance, release the button. That is the process of demagnetization. Let's see what we do with this screwdriver. Not a screwdriver, that's a... if you'll notice, I can no longer lift that arbor. That tweezer is demagnetized. This one, it picks up this pin. Now, I don't know whether the pin is magnetized or the tweezer or both. Let's demagnetize the tweezer. There we go. No, I cannot lift that pin. Let's talk about this describer. Let's do the same thing here. We push the button, we draw it out. That's all there is to it. Simple and easy. No particular problem. We can't stick to any of these things. While I'm here, I believe I'll do the same thing for the tip of my plier, and another plier, and a couple of screwdrivers here. We can do them, a couple of them at a time. We don't have to do this individually. That's it. That's all there is to it. Now, only hard, high-carbon steels ordinarily are magnetizable. These tweezers are very good steel. All of these tools are very good steel. They can be magnetized or become magnetized. We become magnetized by being exposed to a magnetic field. Now, if I want to magnetize, let's say, the butt of this tweezer, I slip that into the field and touch the button and don't draw it out. If, by probability, I release that button while we're going through the crest of one of the cycles of the alternating current, this tweezer will be magnetized. And if you notice here, I can lift that scriber. I magnetized it. I can go back in the same instrument, and by holding the button down, drawing it out, the magnetism is gone. We're completely free. Let's see if we got it on both ends. Yes, we did. So that's the simplicity of dealing with magnetism. If this is a watch, you slip it in there, hit the button, pull it out some distance, release the button. That's all there is to it. If you tamper around with it, if you turn the button loose before you're a distance from it, or if you release the button while you're in there, you literally charge it magnetically rather than discharge it. We'll pause here and remove the demagnetizer and continue on. Let's look at the depthing tool. This is a depthing tool that we used in an earlier tape. Let's pull these runners out something like this, and we'll slip these out a bit further. This particular adjustment right here increases or decreases the space between the runners. I'll move this rather dramatically so you can see that that closes up, opens up. The runners that I have turned inward are female centers, and let's sit these two runners about equally spaced from each other. Now let's take a measurement off of this movement. I commented that we dropped one wheel. Now we're back in that. We have the escape wheel out in our hand. Let's place a nut on here to keep that in place. And let's make let's set the depthing tool up for the distance between the escape wheel shaft and, can we see this? Between the arbor that our crutch is on. The crutch, the escapement anchor, and the crutch is on this arbor. We will set this up to these two dimensions. Got a little problem. I need to get the reflection off of that just a mite and see how we are there. Maybe we can handle this right here. And I'll drop down here and take this dimension off of the plate. Now, I'm going to have to put on my eye loop here, my glasses and eye loop, and look at this close. Well, I have the problem in my tapes getting the cap in the way. It's winter time here. This is 27th day of November 1986. It's a bleak day in Austin, Texas, and when you're bald-headed, you wear a cap to conserve body heat. Now, I have these the spacing between the escape wheel and its anchor transferred to the tips of the depthing tool. Now, that says that I should be able to set that escapement in here and put it into operation. Let's see how we can do that. Bring that up. We need a zero clearance, but not a bind in this, so we can spin this wheel. And we need the escapement anchor in there. In order to do that, we need to turn the crutch back out of the way. Now, we're miles away from the beat adjustment being correct at that point. And let's set the anchor in place. Okay, now let's turn around and take a look. See if we can find our place here. If we look at this, the escape wheel is not centered on the anchor at this point. So I'll just loosen these two runners, and we'll move the anchor over and see that we're tight there, and we are. Now let's look at the escapement action. At that point, I cannot escape. I'm placing just ever so slight force here. I cannot escape. That's too close. So I will increase the distance. I'll increase the pivot distance here and see what we have. All right, at that point we can escape. And let's look a little further. Let's turn this up about like this and see how we do. And we see that we can escape just as if we were in the clock movement. That is approximately the spacing. That is approximately the spacing that we need for this escapement to work out perfectly when we reassemble a movement. If you have repairs or adjustment that's to be made on escapement parts, the depthing tool is a great tool to use for that work. Let's see how that compares to the pivot spacing that we had on the movement. It looks like here that we're probably about 0.010 of an inch wider than the pivot space that was on the front plate of the movement. Now we can only adjust the bridge for this piece on the back side of the movement. Let's see what the situation is. The escape wheel, we'll have to look closer again. The escape wheel sits in the movement like this. The wheel is nearer the rear plate than it is the front plate. And we need to increase this total spacing about 0.010 of an inch over the value that we found in the front plate. Now, if we raise the bridge that is to the back side, we will have to raise it a little more than 0.010 of an inch because this portion of the wheel does not rise as much as the adjustment there. All right? This movement here, the slack, the clearance, the running clearance in this pivot permits us to raise or lower the bridge on that end that would affect the clearance at this end of the wheel. I should have said this pivot, the anchor pivot. Now, if we place the anchor on, not the anchor, place the bridge on, and see where the pivot lands on that. Let's set one of these a little longer than the other because the bridge is an overlay on the plate, and let's see what we can find. I'll lay this up here by finger, set this onto the plate, and take a look. I'll land down here, and what do I find when I look at the bridge? I don't think that you could see this in the photograph, but I found that the top edge of this bridge, right here, top edge of the bridge, the two sides, will be approximately flush with the top of the plate, or just a mite higher, or just a bit higher. So when I assemble this, if I go to the position, if I assemble this bridge, or this, yes, the bridge and this, if I assemble this just ever so slightly higher than the surface of this plate here, it says my escapement should be in order. Let's try that and see what we get. Remember now, we have to replace the escape wheel. We have to loosen this, go back in with the escape wheel. We may not have to take the nuts completely off. We never did put the second one back on. We go in here and see what we can do in getting this back in place. Got the fourth wheel in place. Got the escape wheel in place. There we are. Let me cut the camera for a moment. Let's continue and assemble the anchor in place. Remember that when we had this in the depthing tool, that we moved the crutch around considerable distance. We'll just leave that around the top for the time being, and we'll set the bridge in place. No, we can't do that. We have to get the crutch out below the bridge. So here we go again. Crutch is below the bridge. Pivot is in the bridge, and let's at this point place one of the screws in place. All right. We'll run this down in kind of a snug position. Now let's take a look. I'm going to raise the bridge ever so slightly above the surface of this plate, the thing that we judged in the depthing tool a few moments ago. Snug that up, and we'll put in the second screw here. I just have a real problem in assembling these things so that it can be seen in the camera. As a matter of fact, I can't get that one started. Let's try moving the bridge again. There we go. Now, let's inspect this situation. I'm a little below the position that we judged it would be correct for the escapement. So we raise the bridge ever so slightly and snug that screw, and do likewise over here. And about there. Now let's kind of tighten these up. At this particular point, we think we have the escapement adjustment about right, and let's look at this. I can move the crutch to that distance, to the right, to here, to the left. So we're obviously not anywhere near being in beat. I'll pull this over a little further and look, and we're a little closer to being approximately centered there. The next thing that I will do is put just a bit of torque on the train over here and see where we escape. I'm looking for the escapement point on either side of plumb, and that appears to be about right. Now the point is this: will we be able to have a functioning movement at that particular point? Let's pull the mainspring up and see what we've got. I pulled up one click there. Let's carry this up one turn. That's a half. That's one turn. That's most of the way down on the mainspring. Turn around here and let's see what we have if we look at the movement. It doesn't appear to continue to tick here. Let's try changing the position of the movement. If I tip it a little bit like that, it does. If we want to know if that escapement is free, let's see if we can continue for a full revolution of the wheel. The thing I'm looking for is this motion right here. Now, if I should look at this a little closer, let's move it like that. If we like, we might set this movement aside and let it run for an hour or so in that in that particular condition. But as we have inspected the movement on assembly, I suspect there is not any need to do that. Let's take off the. No, I don't believe I'll take these off at this point in time. Let's set the dial works in place. Have to move this foot. It's a conflict with the wheel here. Drop it on. Drop on this one. That's wrong. That's wrong. See, there's no pinion for this to mesh with there. It says this one has to be inverted, and the pinion is there for us to mesh with. We have a pinion in place. Put on the C-clip. Most of these C-clips can be pressed on with the fingers. We'll see how this one does. Have to get a tweezer over it. There we go. Got that in place. We would be ready to place the hands on it. While I had my finger around back, I was pushing on that crutch, so we've got considerably off beat again. Looks like this might be about the spot. All right. Let's talk about the pendulum. First, we'll go ahead and place this remaining nut on the plate. If we should allow this plate to get loose with power on the mainspring, that is the end of one nice trapeze movement, because it would literally be a wreck. We'll pull this up a little more right here. Okay, turn around to the back. To assemble here, we go through, turn crosswise, hook up the suspension spring, and we carry the suspension spring up to the chop, to the hanger. Find our pin. May be able to handle this a little better in my fingers. And we have to align the hole on the other side. That pin being tapered, we just push it in to snug it down. Let's see what we have here. We'll hang this off the edge of the workbench so that we can see what happens. And we can see that this movement really wants to run, really wants to go. Mainspring is almost down. And we'll gather the pendulum, latch it in place. Latch this in place, and let me move the camera. Looks as if we have a pile of who knows what down below there, and got a little problem seeing the pendulum. See if we can move some of that. Maybe we can obscure a little of what's below, and we'll start the pendulum for just a minimum amount of motion to sustain oscillation. Let's take a caliper and see if we can measure about what that motion is. Well, we're gaining motion pretty rapidly here. We're swinging about 1 1/8 inch at that point. Let's cut the camera and we'll look at it in a couple of minutes. Returning, I placed a piece of blue paper over some of the things in the background there. The time that the camera was off was approximately a minute 30 seconds. And let's look at this situation again and see about how much we're swinging. We're swinging considerably more now. Upping a little further. And we're gaining motion, steadily gaining motion on the pendulum. At this point, we've come up from about the 1 1/8 that we were talking about to begin with to about 1 5/8 now. If I look up into the escape wheel of the movement, and I can't get the camera on that at this point, but I see that the escape wheel is recoiling rather substantially. That says that we have more than an adequate amount of power, to more than minimum requirement of power to run this, and this movement looks like that it is going quite well. Now the thing that we have is why should we test run this? What will we be doing in a test run? Well, we've determined that we have no irregular frictions in the train. The train is good. The in-play in the individual pivots is good. Let's move the camera up a little. We determined that each of the pivots was good in free order. We had adequate shake. We determined the escapement was correct. Out in the depthing tool, that is the depthing of the escapement, we looked at the beat adjustment before we hung the pendulum in place, and we'd say, what is the purpose for a test run? We can assume with a very, very high degree of accuracy, or with a very high degree of confidence, I should say, that this movement will run, and it will run good. So the sole purpose for a test run following this is to determine the rate, to determine that the pendulum is indeed in proper order. And I would judge that if this movement is run 24 hours, or approximately that, and if the rate is good in that period of time, that a further test run is of really no significant value. The object is this, that we assemble a movement so that we know that it's in order. We know that it will run. We cannot know what that pendulum length has done, or where the rating nut may be at this particular time. We'll deal with some pendulum adjustment in another discussion. But this shows how easy it is to get in and out of a simple movement, and some of the considerations in doing so. Having assembled this movement, we picked it up off of the bench at this point in time, and I've set this into the window of the workshop here. Well, let's just look out at the window and see what's going on here in the country on the JB Ranch. Just outside the window you see a magnolia tree. That tree was planted as a sprout about 19 years ago. It's about 30 or 35 feet high now. It's covered with blooms every spring, and those blooms are in the order of almost a foot in diameter in the spring of the year. Smell very, very sweet. We're very proud of that magnolia tree, and when I'm working in the shop here, I watch it carefully from day to day. Continuing the Huckabee random clock talk, the little movement that we had in the earlier portion of this film that we worked on has been sitting here running for a couple of hours at this point. Of course, it's escaping much faster than its normal operating rate. And what we will do in this portion of the talk, we will talk about the gear train and what relation that has to runtime, pendulum length, and things of the like. So we'll make a setup here and look at this gear train and see what we can find there. Let's go back into the movement that we've been working on and look at the gear train and some of the things in that area. We'll disassemble again here, as we did earlier in the day. We take out the suspension spring, the pendulum rod. We will have to let the mainspring power down, and in the same manner that we did before. I won't go into the detail as much as we did in the earlier photographs. Mainspring power is down. We will slip the movement apart now. Lost my screwdriver here, so I'll have to cut the camera and find another. Back in business. Let's take the ratchet off. I believe with this longer screwdriver, my hand is not in the way of the camera as severe as it was a little earlier. Off goes these items. I think I will leave the dial works in place because the center shaft will remain in place, and it will not serve much purpose for me to remove that portion. The nuts, and we'll spin these off, spin them off, not spend. You can observe that the workman that's familiar with the movement, it's only a minute or two or possibly 3 to completely disassemble the movement. Let's look at this. We're getting the escapement anchor out, leaving the suspension bridge in place. We'll lift out the great wheel, the the second wheel, and we want to deal with the pinion. We want to deal with the pinion on the center wheel, the teeth on the second wheel, the pinion of the second wheel, and the great wheel. Let's ask the question, how long will this movement operate on a single winding of the mainspring? When I say a single winding, I mean from run down to full wound. How many days or how many hours do we have stored? How many hours of operation do we have stored in this mainspring? I've never really looked into this movement before. I don't know. It's a so-called 8-day movement. But let's see what we have when we go into this. I'll cut the camera and make another setup here. We'll come back and then study the result. We've had a lapse of about 5 minutes here while I was doing a little study of this gear train. And let's see what we find. See what the account is. The great wheel, we found when we counted the teeth. I marked a spot here, counted around. We find that the great wheel has 60 teeth. And we enter that as great wheel, 60 teeth. The great wheel, in turn, is meshed into the second wheel pinion. The pinion of the second wheel, which we look at as such. And we counted that pinion, and we find that it has 10. So the second pinion has 10 teeth. If we look at the ratio of 60 to 10, we find a ratio of 6 to 1. 6 to 1. That is, the second wheel will make 6 revolutions for 1 revolution of the great wheel. When the great wheel has made 1 revolution, the second wheel will make 6 revolutions. Now let's look at the second step in this train. The second step of the train is the wheel, the second wheel. We counted this off, and we find that it has 66 teeth. So we enter here, the second wheel is 66 is 66 teeth. And that wheel, in turn, we remember, is in mesh with the center wheel. The center wheel. And as we turned this over and counted the teeth and the having a little trouble with my lighting here, in this wheel, the pinion, the center pinion, has 10 teeth. All right, let's look at the that situation. See if we can bring a little more light up here. The second wheel has 66 teeth. The center pinion has 10 teeth. That is a ratio, 10 into 66 is 6.6 to 1. So we have two ratios, a two-step gear train between the great wheel and the center shaft. That is 6 to 1 and 6.6 to 1. We take the product of those two numbers, the 6 to 1 and the 6.6 to 1. I've written that wrong there. This should be 6.6, not 6.1. 6.6 and 6 gives us 39.6. Now what does this number mean to us? That means that the center wheel of our movement, the center wheel in the movement, namely the minute hand, will turn 39.6 revolutions for one revolution of the great wheel. 39.6 hours will be required to release one turn of mainspring from the barrel. Now, if we take that situation and look at it, let's ask the question of how many turns of mainspring will be required for the clock to run 8 days. How many turns of mainspring will be required to run 8 days if one turn of the spring gets 39.6 hours of operation? Let me cut the camera here and I'll post the figures and then we'll look back again. Let's look at the finding on this. One turn of the mainspring gives us 39.6 hours. Let's try 8 days. 8 is the number of days we want to operate, times 24 hours per day is equal to 192 hours. That's the period of time in 8 days. We find that one turn of the spring is good for 39.6. Therefore, 192 hours divided by 39.6 is equal to 4.85 turns of mainspring. 4.85 turns of mainspring will operate this particular movement 8 days. We saw in the previous work on this movement that one turn of the mainspring, one turn is completely adequate power to operate this movement nicely. So let's say that if we had one turn of the mainspring as a safety factor and we need 4.85 additional turns for 8 days, we need something in the order of 5.85 turns of the mainspring to have good satisfactory power for a full 8 days. All right, let's see what we have in the movement. I haven't looked into this movement before, and I really don't know. I really don't know what we have. I don't know whether we have 4, 5, 6, 7 turns of mainspring, but let's look into that and see how much time we would expect this movement to satisfactorily run on the spring that we have. I intended to turn the camera off and assemble the movement, but just to see how long it takes to do this, you might look on your watch and let's see about how much effort it is to assemble one of these things without too much discussion going along at the same time. we have the gears in place. We drop the plate on top. I have to begin to find the pivot holes for these. The reflection from the light in the window is bothering me a bit here, but in reality I should be able to assemble one of these things approximately in the dark after so many years of this type of work. So let's see what we have. There we have all the train in place. Get some nuts on this. Turn around, pick up a couple more of them. I would imagine that I should be able to assemble one of these things in about 5 minutes. Don't really know. All right, we'll pull these up. And at this point, we'll place on the ratchet. You have to pull the click and click spring back out of the way. Put on the hold down. And I have it on bottom up. That won't work. Now we've got it. And we go into that. See how we do with this longer screwdriver. You may notice that for the most part I don't hold these larger screwdrivers by the handle except to tighten. I hold them by the shank so I can spin them between my fingers. Now the one thing that we have to do is take this bridge off. Really didn't save anything by not taking it off to begin with, because I have to take it off to get the escapement anchor back in place. Possibly we can do that without taking that second screw completely off. No. Yes. There we go. We raise this up. We recall that we set this bridge just a mite above the rear plate was the adjustment point on it. And pick up the other side about the same distance, and we'll tighten this screw. There we are. I guess that didn't take more than 3 or 4 or 5 minutes. Now let's try something. We're in a position now to begin to find out how much running time we have. You know, it's for some reason I don't have a key that'll fit this this clock. This belongs to the AWCI, American Watchmakers Institute. I grade the correspondence course papers for quite a number of the students, and apparently this movement was sent in without the key with it. Maybe it never had one. All right, let's wind it up. I'll put a marker on the key. There's the first turn. Let's call that first turn. Let's see if we can get that marker where we can see it. I don't know. Maybe if we do, maybe we get a little light over here. Black as that marker is to my eye, I'm surprised that I can't pick it up on the camera. Well, that's one turn right here on the key. Let's try the marker out here on this part of the handle. Maybe we can find it out here. That's one turn. We'll call that the safety factor. There's the second turn. There's the third turn. Here's the fourth turn. There's the fifth turn. There's 6, 7. 7 1/4 turns. 7 1/4 turns of mainspring that we have in this particular movement. Now we go back to our numbers here. We have indicated that if we have 5.85 turns, that we're good for 8 days with a 1-turn reserve. We have 7 1/4 turns available. 7 1/4 is the available time. And let me cut the camera here. We'll do a little figuring, and we'll see how long that we would expect this movement to run satisfactorily. The run time is a little greater than I expected. I suspected, as nicely made as this movement is, that we wouldn't have any problem making an 8-day run, but let me show you the figures that come out of this. We need 5.85 turns to run 8 days and have 1 full turn safety factor for to be certain that we won't stop. That's an arbitrary figure that we chose when we saw how it was how nicely it was running here earlier today. If we take the 7 1/4 turns, that is the total winding on the mainspring, minus 1 turn for safety factor, gives us 6 1/4 turns that we can use actively, reliably to power the movement. 6 1/4 times the 39.6 hours that we can get from each turn of the mainspring says that we can run 247 hours, 247.5 hours that we would expect to run reliably on a full wind. If we divide that by 24 hours in a day, we find that this movement will run 10.31 days very reliably without any rewind. That is a very conservative drive system, and one of the things that you would find in that, if the spring is wound, if it was wound not totally hard tight, then the mainspring power force would be more even over the period of time and might even improve the rate situation. Well, what we see from the gear train here is that this movement should have absolutely no problem in reliable operation of at least 10 days between windings. What we find here, it will not go 14 days because we have allowed, you see, an extra turn of mainspring, which we've allowed for safety, is only good for 39.6 hours. If we add 39.6 onto 10.31, we're in the order of approaching 12 days. So it will not run 14 days, but it would run very, very reliable over a period of 8-day time. So that's one of the things that we can do with some simple figures on a gear train. Let's cut the camera, and we'll take another subject matter on gear train ratios. This is an interesting situation to look into in most any clock. And what this says, that the reserve power that's available here is very substantial if the movement is wound each week. And the spring is strong. It is well powered. We saw that when we pulled up the first 1 turn, and how well that the movement was escaping and that the pendulum was gaining motion steadily for the first 3 minutes of operation. We'll cut off and then we'll look at another subject matter. Continuing the discussion of this little trapeze movement, let's ask the question, suppose that I had this movement in hand and I was faced with preparing a pendulum for it, and I have no pendulum available to me. How could I know how long that pendulum would be? Suppose that I would like to mount this in a case and set up the operation, and will it fit the case? Is the length suitable for the case? So let's go into this movement and see what the length of the pendulum has to be for satisfactory operation and a good timekeeping rate on this movement. Let's imagine I have the pendulum over here. We looked at it this morning, but for the most part I didn't pay any real significant attention to the length on it. It looked to me like that it was, stretch it out here between my hands, looked like it might have been about a foot long, but I don't really know what that is. Let's determine the length of the pendulum and do some talk about that. Again, we'll disassemble this movement. It's been said that old Huckabee gets a hold of one of these movements, he'll wear it out, taking it apart, putting it back together. Well, it's really like this. I find this situation so easy that it doesn't bother me to disassemble, reassemble. Incidentally, while the camera was off there a moment ago, I let the mainspring down. So we're not expecting this thing to go zap and destroy the movement. I wish I had timed how long it takes to disassemble this. And some of you may have looked at your watch. The viewer may have looked at the watch when I was putting this together there before and arrived at some amount of time it was required for me to assemble it. I suppose it was in the order of 3 to 5 minutes. I don't really know. In the many years of clockmaking, I have never ceased to enjoy working on clock movements. This is one of the great pleasures of life, is when a person's work is enjoyable. And indeed, clockmaking is work and enjoyable to me. Let's take out things that don't count for this particular thing, particular thought and study. The thing we want to do is to find the length of the pendulum. Find the length of the pendulum if we have to provide a pendulum. In order to do that, we have to know how many times, how many beats per hour that this pendulum will swing. How many beats per hour? In order to do this, I have to know the teeth in the center wheel. The center pinion underneath here is unimportant to us in this information. We've already used that in dealing with the mainspring. But I need to know the tooth count here. I need to know the pinion count here. I need to know the tooth count here. I need to know the pinion count here and the number of teeth in the escape wheel. Well, to prevent burning up a lot of your time while I'm doing this, I'll cut the camera off. I'll count these teeth and label this and be back here in a few minutes. There's been a lapse of something like 5 or 10 minutes while I was looking at these wheel teeth, and let's see what we find here. We find that the center wheel, this is the one that drives the minute shaft, has 84 teeth. So the center wheel is 84 teeth, and we found that the fourth wheel, this next wheel in the train, has, it's written on this side, is 70 teeth. So we say 84 times 70 times, and we look at the escape wheel, and we find that the escape wheel has 30 teeth. So it's 84 times 70 times 30, and our escapement anchor has 2 prongs on it, has 2 tips on the escapement anchor. Why does this enter into the calculation of what's happening in the gear train? Pure and simple, a tooth of the escape wheel must pass both of these anchor tips. So that says it requires 2 beats of the pendulum, not 2 round trips, but 2 changes of direction. Requires 2 beats of the pendulum to escape 1 tooth. So we say times 2. Now we divide that by the product of the pinions. This is the product of the center wheel. Get the pointer here. Product of the center wheel, 84. Product of the fourth wheel, which is 70, 84 times 70, and the escape wheel, which is 30, and the two escapement pallets. It's 84 times 70 times 30 times 2. We look at the escape wheel pinion. It has 7 teeth, and the fourth wheel also has 7 teeth on the pinion. So let's compute this mathematically and see what we get. The product of all the wheels and the escapement anchor, that is the projections on it, the projections of all the wheels and the projections of the escapement anchor, divided by the product of the pinions. That comes out to be 7,200. 7,200 is the figure that we get on that. Now that is 7,200 beats per hour. We're talking about 1 hour. We're talking about 1 hour of the center wheel, 1 revolution. 1 hour of that wheel is 1 revolution. And the pendulum must change its direction, that is a beat, calling a beat, 1 change of direction, 7,200 times in an hour. Let's take that 7,200 and divide that by the number of seconds, the number of minutes that's in the hour, divided by 60 minutes in the hour, and this gives us 120 beats per minute. So this particular clock is 120 beats per minute. Now, the mathematics of arriving at the pendulum length is pretty cumbersome. And if you're not adept as a mathematician, this may present a problem to you. And I would counsel you here to refer to some good handbook on that has a good section on pendulums and a table, and consult that table for your 7,200 beats per hour or 120 beats per minute, and find the pendulum length. Now, when we find the pendulum length, we find a theoretical length. The theoretical length and the practical length are two diversely different situations. Now, I want to find the theoretical length for you and then give you some practical direction on top of this. Here is a sheet that I provide to most of the student clockmakers that's taking the AWCI correspondence course. I calculated this a long time ago. I've got a date down here on this, but I calculated this a long time ago. I use a copy of this in my shop. This says table of pendulum lengths, beat rate per hour, per minute, per second. Pendulum length in millimeters and inches. And the length, the change that is required, the change in length that's required in millimeters or in inches to change the rate of that movement 1 minute per day. That is, we can look at this table. We can tell if a clock is off 5 minutes per day, let's say fast, we need to slow it down. We can look in this table and see how much we need to change the nut, how much distance we need to change the ball of the pendulum to bring us into rate. If we look down this, there's just some loose numbers down here. Here's 3,600, that's 60 beats per minute. The period is 1 second. The metric length of the pendulum is 993.9 millimeters. The length in inches is 39.13 for the seconds beat pendulum. If we need to increase or decrease the length of that pendulum for 1 minute a day, it takes 1.38 millimeters to change that rate a minute a day. Or if we're measuring in thousandths per inch, thousandths of an inch, then it is 54 thousandths will change the rate a minute a day. We can either measure to a mark on the pendulum, or if we know the pitch of the thread on the nut that supports the ball, then we can go to turns count. But let's use the second sheet of this table and come in a little easier to what we're looking for. This says pendulum beat rate per hour and length in inches. This says calculated by J.M. Huckabee, February 24th, 1984. So let's look down this. We look down this, we're looking for this begins at 3600 per hour. We're getting faster here, right at this point is the 7200. It says the pendulum must be 9.78 inches long. 9 inches, 780 thousandths. That is just a tad over 9 3/4 inches that the pendulum has to be. Now the question is, what is a 9 3/4 inch pendulum? Let me cut the camera and we'll get the pendulum that is associated with this clock. We'll measure that and we'll look and we'll see and how that we rationalize this 9 3/4 inches, approximately 9 3/4 inches for this pendulum, and how that it fits to the clock that we have. I don't know what this pendulum measures, but we can look at it and we can see what the situation is. Back onto the pendulum, let's take a look at the one that's associated